In this video, I am going to walk you through the boiling point elevation calculations. First of all, in your lab report, it asks you to describe the way in which you can make or create 4 50 milliliter solutions of sodium chloride at these molalities, 0.25 molal, 0.5, 1, and 2 molals. Be sure to show the math and how you calculated the mass of sodium chloride used. Also, assume a water density of 1 gram per milliliter. Now, here are the formulas that you're going to need. The little m, molal, and it's supposed to be kind of slanted to change it from this one here, but I spelled this out as a mass. But this is molal, and by definition, molal is equal to the moles of your solute, which is NaCl in this case, over kilograms of solvent, which is water. Now, I am given the molal, and indirectly, I am given the mass of the water, and I can rearrange this equation to solve for moles of sodium chloride. So I can rearrange this to get moles of sodium chloride is equal to the molal, so 0.25, 0.5, 1, 2, etc., multiplied by the mass of my solvent, which is H2O. Now, how do I figure out the kilograms of water? Since I already have the molal, all I need is this piece here to find the moles of sodium chloride. Well, we have, in the problem, we're told 50 milliliter solutions. So 50 milliliters, we assume that this is also the volume of the water, and we have a density of 1 gram per milliliter. Since we have a density and a volume, we can then calculate the mass. We have density and we have the volume, 50 mils, so then we can figure out the mass. Once we have the mass, note that this is actually in grams. So I have density in gram per mil multiplied by milliliters. My milliliters will cancel, leaving me with grams. And therefore the mass is going to be in grams. But the formula for molality wants the mass in kilograms. And that is where this is going to come in handy. So this is your conversion factor to go from grams to kilograms. When we go from grams to kilograms, we divide by 1,000, and so we move the decimal place to the left 3 times. So whatever you get for the mass here, move the decimal place three places to the left, and that will be your mass in kilograms. Now that you have the mass in kilograms, you have the molality because it's given to you. You can calculate the moles of sodium chloride. But we want to figure out the mass of sodium chloride, not just the moles. But once we have the moles, remember that we can figure out the mass by multiplying the moles of a substance by its molar mass. So you will have to figure out what the molar mass of sodium chloride is, multiply that by the moles to get the grams of sodium chloride. You find the molar mass, just as a review, by going to the periodic table, finding the mass of 1 sodium and 1 chlorine, add them together, and that's the mass of your sodium chloride. Multiply that by the moles you get from this equation here to get the mass in grams. And that's part 1. Then you are asked to figure out the boiling point, to fill out the boiling point for each of these molalities. Now, you're not actually doing this lab, so this data is provided for you, so you need to write the boiling points down, and the boiling points have to correspond to the molality of each solution. Then it asks you to graph the molality of sodium chloride versus the boiling point. And this is kind of what it would look like. You will have molality at the bottom, boiling point in the y-axis, so molality in the x-axis. Make sure that you label the axes, put a title to your graph, and then just like you are shown in the video, do the graphing video, do a linear fit to your data and extend or extrapolate that fit until it crosses the y-axis. Now this line is supposed to cross here at 100 degrees because that's where pure water crosses. However, we don't have pure water, so it crosses a little above it, just a little different. So we can see where, now if the molality is 0, right, if we have no salt, this is supposed to cross at 100. But for experimental error and such, we don't quite get to 100 degrees Celsius. But you need to graph and you need to include this in your lab report. Make sure that you watch the video on how to do the graphing. Then, using the best fit line, so go back over here, use this best fit line, and I will show you also how to figure out the equation of this line. You can do it either way. You can either solve for the equation or estimate from the graph. But using the best fit line, predict the boiling temperatures for a 0.75 molal and 1.5 molal solution. So you can estimate from the graph or use the equation of the line. How would you do it from the graph? Well, where's the molality that's given to me? 0.75, that's about halfway between these two. So 0.5 is here, 1 is here, so 0.75 is going to be right here. You draw a line upwards till you cross to reach that line, the best fit, and then you draw, a line horizontally to figure out where the boiling point falls here. So find the molality here, go up till you hit the line, and then go parallel till you cross the boiling point and estimate what that temperature is going to be. Then fill them out here as the predicted boiling points of these solutions. Describe the way in which you can make the two 100 milliliter solutions of sodium nitrate that were used in the previous table with these molalities, 0.75 and 1.5. Now this follows exactly the same, and I have NaCl here, but it's supposed to be sodium nitrate, so NaNO3, and it follows the exact same calculation as the one for sodium chloride, except this is supposed to be NaNO3. I made a mistake here. So when you go to figure out the actual mass of, this is for the mass of water, but when you figure out the mass of sodium nitrate, you are going to find the molar mass of NaNO3, and that will be different than NaCl because you will have 1 sodium, 1 nitrogen, and 3 oxygens to add all together. But other than that, everything else, all these calculations are exactly the same. You just have a slightly different molality for both of these and different molar masses. And the solution has a different volume. So instead of 50, we have 100. The density assumed the same, so 1 gram per mil. The molality is 0.75 or 1.5. And then the molar mass is going to be the mass of NaNO3 instead of NaCl. Then, if you were to do this in the laboratory, you would actually measure the boiling temperatures of these two solutions with 0.75 molal and 1.5 molals. But since you're not, we're giving you these boiling points in degrees Celsius. Then you are supposed to calculate the percent error between your predicted, right? So from the best fit line, your experimental value for those boiling points of the solution and the actual boiling points that were given to you in the previous slide that I had. And you will be using this formula to calculate the percent error, the accepted value, the values in the previous slide, minus the experimental value, those values that you get from the graph by going up till you hit the line and then going across till you hit the y-axis. Those are going to be your experimental values. Divide by the accepted values times 100. Remember that the percent error is always positive, never negative, because this is an absolute value, and absolute values are always positive. Then we get to the last little bit where you have to do a little more in-depth calculations. So when this information is extrapolated, such as for natural solutions, such as seawater, you have several things that change. First, the dissolved materials cause a boiling point elevation or freezing point depression. Then the specific heat capacity, however, and density changes from pure water. So normal water has a specific heat capacity of 4.184 joules per gram degree Celsius and a density of 1 gram per milliliter. Seawater has specific heat capacity of 3.993 joules per gram degree Celsius and a density of 1.02 gram per mil. So with this information, what is the energy difference, between heating 50 milliliters of fresh water and 50 milliliters of seawater? So from freezing, 0 degrees from fresh water and minus 1.8 degrees for seawater, up to 25 degrees. So show all calculations. Use this formula to do the calculations where m is the mass in grams. Now remember, assume, once again, well, you don't have to assume. For water, pure water, it's given to you that the density is 1 gram per mil, but for the seawater is 1.02 grams per mil. So just like we did in the previous slides, use these two pieces of data to calculate the mass of pure water and calculate the mass of seawater. This C is a specific heat capacity, and that's given to you as well. For pure water is 4.184, whereas for seawater is 3.993. And then it's multiplied, so those two numbers are multiplied together and then multiplied by the final temperature minus initial temperature. The final temperature is where you end up, so in this case, we're going from freezing to 25 degrees. So for pure water, you're going from 0 to 25. That means your final temperature is going to be 25 and your initial is going to be 0. For seawater, you're going from minus 1.8 to 25. So this is going to be 25 minus a minus 1.8, which becomes 25 plus, so a minus and a minus make a plus. So 25 plus 1.8 instead of a negative. Now I've got this little example here set up for you just to kind of show you how to use this formula. Here's some of the data. Now this data is not what is up here. This is just to show you what a calculation would look like for this formula. So let's say I have a mass of pure water and it's 150 grams. The heat capacity or specific heat capacity of water, pure water, is 4.184 joules per gram degree Celsius, like it's given here. The T final is 78 degrees, then T initial is 35 degrees. Okay, so here's my formula. Now let's just plug in the numbers. So the mass, is 250, not 150. Must have hit the wrong button there. So 250 grams times my C, which is 4.184, joules per gram degree Celsius, times my T final, 78 degrees, minus the T initial, which is 35. Now, the easiest way to do this is do the subtraction inside the parentheses first and then do the multiplication. So that's what I did here. 250 times 4.184 times 78 minus 35 is 43, so I put 43. Then if you multiply these three numbers together, you get 44,978 joules. Now this is the amount of heat that is required, or energy that is required, to raise the temperature of 250 grams of water from 35 degrees to 78 degrees. Now, in your problem here, note that it's asking you to calculate the energy difference. So you're going to do this twice. You're going to find how much energy is needed to raise the temperature of pure water from 0 to 25, and how much energy is required to raise the temperature of seawater from minus 1.8 to 25. And then take the difference between those two because it's asking for the energy difference. So you will use this twice, once for the pure water, once for the seawater, and then you will take the difference in joules between the two, and that's going to be your answer for this part. And lastly, you have this question: would the molarity and molality of the solutions used in this experiment be the same or different, and why? So think about what the formulas are. This is molality, this is molarity. They both have moles, but they differ in the way they look at solvent and solution. So the moles of solute are the same for both. But for molals, we look at just the mass of the solvent, whereas for molarity, we look to liters of solution. Now, if you have to think about, do I have pure water or do I have, right? There's some assumptions that we have to make. If these things are to be the same, we have to make assumptions. If we don't make these assumptions, they will be different. So is it liters of solution or is it liters of water? Is it the volume of your water? Is it the same as basically the same as kilograms of water because of the density? So are we basically talking about pure water, or are we talking about the seawater type, right? Not impure water, water that's got minerals dissociated or dissolved in it. So you think about what that entails and then try and answer this question.